Alright guys, we're going to go through problem 11, predict the product for the following reaction. And we have this reactant in this box right here. It's a cyclo compound with a good leaving group as our bromine, good leaving group. And we're going to look at the reactants to figure out what kind of reaction we have. So looking at the reactant, we have sodium ethoxide. When you see an oxide with an "ide" at the end, that means you have an O negative. Sodium's obviously our element for the periodic table, and it's usually a positive charge when it's in organic chemistry. So that makes up for the neutral of our compound, neutrality of it. And our ethoxide is just an ethyl group, so it's the two carbons attached to it, that O negative. That negative charge in metal are huge hints that we have a strong nucleophile. And strong nucleophiles eliminate our available reactions to just the ones with 2 at the end, because we need a weak nucleophile for E1 and SN1. So now we have the option of this just being SN2 or E2. We can look at the solvent to see which one's better, or the best way to look at the carbon we have available attached to that leaving group. And on this case, we're acting on a tertiary group. And tertiaries do not like SN2. So we can say that we're likely going to have an E2 reaction because E2s love tertiaries. The only time we ever have to go more in depth than that is when it's a secondary. And then we have to look at the solvent to see whether it's protic, aprotic, or if it's heated, if the product is being heated. If something's heated, it's gonna favor elimination. If it's cold, it's gonna favor addition or SN2. Okay, so we're gonna get a strong nucleophile, this ethoxide, and it's gonna do the E2 reaction. So it ends up taking an H on the opposite side. Then that H donates its old electrons here, and we have our leaving group leave all in one step. We can also have it happen with the hydrogens nearby. The only important part is that the hydrogen be on the opposite plane as the bromine. So if it's wedged, we want it to be dashed. If it was dashed, we'd want it to be wedged. On the sides available here, we also have the wedged hydrogen up there. We would take the dashed one because it has to be anti to this guy. Now, this one, since it's dashed as well, these two are our two main candidates. If this was wedged, we would not have an E2 mechanism. Okay, so we have those two options. Let's draw them out. So in both cases, you have the bromide leaving, and then you can have this leaving in one case. We'll say that leaves the bond here. And we'll do the other double bond over here. That can be this hydrogen as well, because these things will be symmetrical, so they're basically the same thing if I drew the double bond here as well. Okay, so now we have to decide whether it's Zatev or Hoffman. And since this is not a bulky base like T-butyl, we know it's going to be a Zatev or more substituted double bond. Now looking at our molecule again. So which one of these is more substituted? We count the carbons that are nearby the vinyl carbons. So how many allylic carbons there are. So the first one, let's look at the red. We have these vinyl next to that double bond, and these two. So we have 3 aromatic carbon, or allylic carbons. And for the one down the middle, we have 1, 2, 3, 4. So this is our the purple's our Zatev, and the red is our Hoffman. Meaning we'll probably be favoring answer D. Let's see. C is our Hoffman product if our base was bulky. B is our SN2 if we wanted that. We're not going to get it in this case though because we're acting on a tertiary. A is a substitution, but they didn't flip the stereochemistry. E is just saying no reaction, and F is an inversion. But obviously we're going to have D here.